So let's start with the solutions first. We have two masses. M1 is 2 kilograms. Its velocity is given. So the momentum of the first mass is 6 x hat plus 8 y hat kilogram meters per second. This is P1. The momentum of the second mass, its mass is 3 kilograms. Its velocity is 2 meters per second in the y hat direction, so it is 6 kilogram meters per second in the y hat direction. The total momentum of the system, 6 in the x hat direction plus 14 in the y hat direction, kilogram meters per second. The total mass of the object is 5 kilograms. You just divide them. So the velocity of the final system is the total momentum divided by the total mass, 6 over 5 in the x hat plus 14 over 5 in the y hat meters per second. This is the final velocity of the system. Now the kinetic energy loss, V1 squared is just 25 meters per second squared. V2 squared is 4 meters per second. No, V1 squared is, yes, 4 meters per second squared. So the initial kinetic energy is 1 over 2. M1 is 2 kilograms. V1 squared is 25 meters squared per second squared plus 1 over 2 times 3 kilogram times 4 meters squared per second squared. So this gives 25 plus 6, 31 joules. This is the initial kinetic energy. The final kinetic energy is 1 over 2. The total mass is 5 kilograms. The velocity squared is 1 over 5. Well, if you just take the square, 36 plus 164 square root meters squared per second squared. So you can just leave it like this. I mean, in such quizzes, if you don't have the calculator, just leave it like that. So the change in the kinetic energy is just the difference of the two. Again, the units should be there. Any questions on the quiz? Okay. So let's start with our subject today. Arada bulur. Now, this week and next week, we will be studying rotations. So some of the things that we will try to understand, I have a few videos for you. So this is one hurricane close to the US. I want you to pay attention to in which direction it rotates. If I have internet access. Yeah, I have wireless. Well, this is another one. Yeah. So this is in the clockwise direction. This is a hurricane close to Australia. Yes. This is close to the US. This rotates in counterclockwise direction. So all hurricanes close to in the northern hemisphere, they rotate in the counterclockwise direction. In the southern hemisphere, like this one, they rotate in the clockwise direction. And well, this is also nice. This is news about a hurricane in the southern hemisphere. And you see that it is rotating in the counterclockwise direction. This is some news channel. And since it's supposed to be a hurricane in the southern hemisphere, this is definitely a wrong photo. The hurricane in the southern hemisphere, they do not rotate in this direction. They have to be rotating in the other direction. So they are making some news about one hurricane and using the picture of another hurricane. Well, hurricanes are kind of large-scale phenomena, but we can see the same phenomena in smaller scales too. I mean, if you are washing the dishes, you would probably see that as the water goes away from the sink, it rotates in one direction, and it is always the same direction. So this is water leaving out of the tub, and it doesn't rotate at all. So, okay, this is another. This is in Australia. That is what we had seen. So it is not so clear which direction it is rotating here. So if you look at the bubbles, they will start rotating soon. So now it starts rotating. And this was in the clockwise direction. You see, it's rotating in the clockwise direction. And here we see another, this is a pool. They are emptying the pool. Well, it's kind of impressive, the picture. So it is rotating in the counterclockwise direction. That is one of the phenomena that we will be trying to understand. Hopefully, at the end of this week, we will be able to explain why the water and the hurricanes rotate in one direction in the northern hemisphere, and they rotate in the other direction in the southern hemisphere. Okay. Now, and how many of you are able to ride a bike? Can you ride a bike? Okay, there's quite a number of you. And you should have probably observed one phenomena. Unless you have special talents and you are an acrobat, you will not be able to stay on the bike if the bike is not moving. You will just fall down. And if the bike is moving with some velocity, the larger the velocity, the better it is, the more stable it is. So you have experienced that, right? Yes. Why? We will see. Yeah. We will see how angular momentum causes that stability. Yeah, that thing. We will see that. And another thing, if you have ever seen somebody riding a bike without holding the wheel, the steer, you'll see that they can turn around. They can turn to the left, turn to the right. If they just lean to the right, the bike doesn't fall to the right, but it just rotates to the right. So we will also try to understand how that happens. Let us have our experiment. Okay, so first I will look at what we have done until now, since our first lecture. Because we will be repeating the same thing. Until now we have been mainly studying translational motion. But we will be dealing with we will be redoing everything for rotational motion now in the following 2 weeks. So first what we did was we had studied kinematics. That is essentially how do we describe the state of the system. Now for the time being, when we are talking about, until now at least, when we were talking about the state of the system, we talked about its position and velocity. And now we described the dynamics. The dynamics was mainly why the state of the system changes. So it is, well, the position changes if it has a velocity, but then the question is, why does the velocity change? So then we started studying the force, and we had the acceleration. We related the acceleration to the external forces. We had then described what is the work done by the forces. If you exert a force on an object, then it might be doing some work, and we had the conserved quantities. This will be the outline of the things that we will be doing also for rotational motion. First, we will start with kinematics. How do we describe the state of a rotating object? So if you have this bike, now in general, a motion will involve both rotations and translation, and it will be quite a complicated motion. If you just take this pen, if you just throw it, it makes projectile motion, and it is rotating at the same time. The axis around which it rotates is also making some translational motion. That would be a complicated description. So first we start with a simpler case. We assume that the axis of rotation in the, let me fix it. The axis of rotation is fixed. It is really fixed. Well, okay. The axis of rotation is fixed. It's not moving. So the only parameter we have in this system, if we want to know what is the orientation of the wheel, is you can just pick any point. Let's just say this point, where you blow air into the tire. And if you tell me the angle that this line, the line connecting the rotation axis to this point makes with the horizontal, if you just tell me that, okay, so this angle is 45 degrees, then I know definitely what the state of my system is. There is no ambiguity. Well, you can have 45 degrees in the upward direction or 45 degrees in the downward direction. And that ambiguity we remove by saying that, okay, if you have an angle in the upward direction, that is a positive angle. If you have an angle in the negative direction, we have a negative angle. Now, this is what we call a rigid body. It is rigid in the sense that its shape doesn't change as it is moving. It has a fixed shape. The axis is fixed, the axis of rotation. And this angle, rather than using 45 degrees, we had already mentioned the radian angles. We use the radian units. Now, the nice thing about this radian units is the way they are defined. They are just the ratio of tool length. So if I have, now let me have this one. Okay, so this is my reference point. So if I rotate it, let's say by 45 degrees, the reference point had moved by a distance L, this arc length, for a radius given by this length. So this length is more or less like 30 degrees, 15 centimeters. This is like 20 centimeters. So in radians, this angle over here is just the ratio of the length of this arc divided by the radius. So if you measure angles in terms of radians, the length of an arc is nothing but the radius times the angle itself, the angle that that arc sees, this theta over there. So the maximum, the horizontal line, 180 degrees, just corresponds to pi radians. 360 degrees corresponds to 2 pi radians. Okay, so this theta is just like our position. In translational motion, we needed to know the position, to know the state of the system, where my object is. And in rotational motion, I need to know this angle theta to specify what is the position of my object, the orientation of my object. Of course, this angle theta can be changing in time. So if the wheel is rotating, it is just changing in time, theta. So we can talk about, just as we did in the translational motion case, we have the average angular velocity. That is the rate of change of theta with time. Or once we have the velocity might be also changing. I start it to rotate, I stop it. And the change in the average angular velocity in a given time, in a unit time, is what we call the average acceleration. This alpha, we denote the angular acceleration usually by alpha, and the average angular velocity usually by this omega. Then just as in the translational motion case, it is just one-to-one copy of everything we did in the translational motion case. We can define the instantaneous angular velocity as the limit that we take this time interval goes to 0. And the instantaneous angular acceleration is again the average acceleration when you are taking the average over an infinitesimal amount of time, very small amount of time. This delta t goes to 0. Again, the definitions are identical to the definitions that we used in the translational motion case. The only difference is that rather than the change in the position, here we are talking about the change in this angle theta. And the units is, well, the angular velocity unit will be radians per second, but not that the radian doesn't really have any unit. It is the ratio of two lengths, so it is unitless. So you can say that the angular velocity has unit radians per second or 1/2. Similarly, angular acceleration has, well, the omega has unit 1/2 divided by second. This is either 1/2 squared or radians per second squared. Well, as the okay, so there is one thing that should be paid attention to: the angular velocity. When we are talking about the translational velocity, we talk about the translational velocity of a single point. But the angular velocity is a property of the whole rigid body. I mean, when you are rotating the wheel, it is not that this part is rotating with some angular velocity, whereas this part is rotating with another angular velocity. At least for a rigid body, all the parts are rotating with the same angular velocity. Angular velocity is more a property of the object as a whole rather than the property of a single point. But of course, the whole thing is made up of many points, many point masses. We can just imagine dividing it into very small objects, each one having a point mass. Each point mass is distributed all over. So we can talk about the velocity of that point mass, each one of the point masses. So if you have an object like this, which is, let's say, rotating in this direction, it is rotating in the counterclockwise sense, then the speed of that point, P, is nothing but the distance it covers in a given amount of time. But we know that L, the distance it covers, is nothing but r times theta, or r times the change in theta, divided by dt. But this ratio is nothing but the angular velocity. So the linear velocity of a point on our rigid body, this point, is nothing but the radius of that object from the axis of rotation. That is, r is the distance of that point from the axis of rotation. Well, this is quite a flat object, but you can imagine, well, let's say this book, which is not so flat. I can just imagine that it is rotating around this axis. That if I want to find the linear velocity, the translational speed of this point, let's say, what that capital R is the distance of that point from this axis. So you just draw a perpendicular line from that point to the axis of rotation. It is and the length of that line is what is the R over there. Or if I take, let's say, this point, then that capital R is again this distance. In this case, it is this distance. In this case, it is this distance, the capital R. And every point on my rigid body, as it's rotating, is actually doing rotational motion, circular motion, because if you imagine I have an object, it is rotating around this axis in this direction. Now this point over here will be making not necessarily uniform, but definitely a circular motion around this point, this is r, with velocity, with speed given by omega r. If I take this point will be doing some circular motion around this point, and this is my r prime. V prime would be omega times r prime. R and r prime depends on which point I'm studying, whereas omega is a property of the object as a whole. It is the same for any point on my object. Now, since they are making circular motion with the same angular velocity, I can talk about the frequency of rotations. That is how many rotations my object makes in 1 second. So it is one rotation is just 2 pi. So frequency is just defined as the angular velocity divided by 2 pi. And the period is just how long it takes for it to complete one revolution. Well, one revolution corresponds to a radiance of 2 pi. It covers 2 pi radians with angular velocity omega. So the period of the object is 2 pi over omega. Now, in this picture, as my objects are rotating, we had already seen that any object that is doing circular motion has an acceleration, a radial acceleration. The radial acceleration given by the acceleration of an object making circular motion. The radial one is speed squared divided by r. Or, in terms of the angular frequency, we can write it omega squared r. But if my object is, let's just take this one. It is rotating. It can be rotating at a constant angular velocity. Or I can just imagine that initially it has zero angular velocity. Then it has an angular acceleration. It starts going faster, faster, and faster. In this case, if you just imagine any point, initially its translational velocity is 0. As my object is starting to accelerate, as my object starts to rotate, it gains some tangential velocity. It gains speed in the tangential direction. As my object starts to rotate faster and faster, its speed is also increasing. So it is not just, well, this is the angular, the acceleration, the translational acceleration of a point toward the center. This acceleration doesn't cause the speed to increase. It only changes the direction of the velocity. But there's also the other component, the tangential acceleration. Well, the speed is given by the angular velocity times r. For a rigid body, r, that is the distance from the axis of rotation, is constant. It doesn't change. So it is, if the speed is changing, the only reason will be the change in the angular velocity. So the change in the angular velocity is nothing but its angular acceleration. So the tangential acceleration of any point will be alpha times r. So if you just imagine this object, this point, as my object is accelerating in this direction, it has a radial acceleration towards this point. This is the point around which my object is rotating. Furthermore, it will have a tangential acceleration. These are at right angles to each other. And the tangential acceleration, it will have a tangential acceleration only if there is an angular acceleration over there. And this will cause the speed of my point to change. Okay, so let me just give you one more information that will hopefully puzzle you. Will create question marks in your mind, so you can think during the break. Now, if I'm rotating this object, it has some angular velocity. And, well, that's a number, the angular velocity. And when we are talking about rotation, we say that, okay, this object has such and such angular velocity around this axis. This is the rotation axis. So when we are describing the rotation of this wheel, we are giving you two information. One is the magnitude is a number that we call the angular velocity. And the second information that we are giving you is the axis of rotation. So we are saying that it is rotating around this axis. So an axis defines a direction. But it defines two directions, in fact. One is this direction, the other one is this direction. But if we can fix a convention to choose one direction, so when we are talking about angular velocity, we are giving you a magnitude and a direction. And the quantities that have a magnitude and a direction are called, yes, angular velocity is a vector. It's not just a number. And well, of course, we have to fix a convention to determine the direction of the angular velocity, and that is how we use the right-hand rule. Just take your right hand, curl your fingers in the direction of the rotation of your object, so your thumb points in the direction of the angular velocity. So as my wheel is rotating in this direction, it is angular velocity points in this direction. If it is rotating in the other direction, then the angular velocity is pointing in this direction. It is a vector. The magnitude of that vector we had defined as the rate of change of the angle theta. The rate of change of the angle theta over here. And the direction is found by the right-hand rule. So that specifies our vector uniquely. Angular velocity is a vector. So any questions before we give a break? So the direction of the angular velocity is along the axis of rotation. So in this example, it can be either pointing in this direction or pointing in this direction. So it's one of those directions. So it's the definition. To determine which one, you just curl your fingers around the axis of rotation. You grab the axis of rotation such that your fingers point in the direction that your rigid body is rotating. So if my rigid body is rotating in this direction, well, this is the axis of rotation. If I grab the axis of rotation such that my fingers are pointing in the direction of rotation, my thumb points in the direction of angular velocity. That is how we define it. If I grab it the other way around, it will be wrong because my fingers are not pointing in the direction of rotation, in the direction that the objects are moving. If my wheel is rotating in this direction, well, then my fingers, they go around my rigid body. So my thumb points in this direction. So in this case, the angular velocity points in this direction. We will see what will be the use of this direction. Okay, see you in 10 minutes.